Now the divisibility properties, let's connect with polynomials. So this session is about connecting the divisibility properties as learnt in the session with polynomials. What happens when we divide a polynomial with the other polynomial? If it is numbers, we have the concept through numbers, but if it is polynomials, we have the same concept as learned through polynomials. So today's session is about divisibility properties connected with polynomials. So let's see how we get the divisibility property through the polynomials. Say for example, I have p of x when divided with q of x, the quotient f of x divided by g of x, the quotient is say q of x and the remainder is r of x. That is, when I divide g of x polynomial with the function f of x, then I get my quotient, which is q of x, and then I get my r of x, which is the remainder, is how we understand the divisibility connected with polynomials. And interestingly, here the property says dividend is divisor into quotient plus remainder. Therefore, using this divisibility property, which is called division algorithm, let's try to see how the polynomials get connected respectively. Dividend in this case being the polynomial which is being divided is equal to the polynomial which gets divided into q of x plus r of x, is how we understand, provided with the condition that 0 less than or equal to the remainder less than the divisor, which is g of x, is how we understand the division algorithm for the polynomials f of x by g of x, or f of x divided by g of x. Divisibility properties connected with polynomials f of x and g of x. Now the continued session is about finding the remainder when a polynomial is divided by another polynomial. So this session will discuss about how we can find the quotient and the remainder for the polynomials which are divided with each other. To start with, finding the remainder. Let's take some example polynomials for understanding this concept more better. For example, I have a polynomial p of x, which is x cubed plus 3x squared plus 3x plus 1, which is divided by another polynomial x plus 1. And I would like to find the quotient and the remainder for this polynomial p of x being divided by another polynomial x plus 1. As we know that the long division method for dividing the polynomials is with the dividend taken in the middle, x cubed plus 3x squared plus 3x plus 1, and the divisor which is taken on the left, is how we start with the construction process. Now continuing with this, I have x cubed which can be filled up by multiplying x with x squared, so that I get x times of x squared, which is x cubed, and 1 times of x squared, which is x squared. And then I subtract with the change of signs, this get cancelled, and I get this to be 3x squared minus x squared is 2x squared, with the other two terms drop down directly from the given expression. Continuing in the same process, I have 2x squared which can be satisfied by multiplying x with 2x. So the quotient gets added up with 2x, which when multiplied with x gives me 2x squared plus 2x. And then on further subtraction, in the same process, gives me with change of sign 2x squared and 2x squared getting cancelled, and 3x minus 2x is x plus 1. So finally, this is the term where I end up because I don't have any other term, or I can take plus 1, so that 1 times of x is x and 1 times of 1 is 1, which on further subtraction gives me the change of signs and then cancel to give me the final answer as 0. So with the end of this, I understand that this is my q of x and this is my r of x. Is how we identify the remainder and the quotient for the given polynomials divided with each other. The long division method is what we call this. Therefore, for the given polynomial p of x equals x cubed plus 3x squared plus 3x plus 1, when divided with the other polynomial x plus 1, I get my quotient q of x is x squared plus 2x plus 1, and I get my remainder r of x is 0. Is how we understand the process of finding the remainder or the quotient using the long division method. Now that we have discussed about division of two polynomials f of x by g of x, it's very important that we just divide a polynomial with the other polynomial through a condition. Let's see what the condition for divisibility of two polynomials is out here, along with the division method of dividing the polynomials as we have seen in the previous session. Condition for divisibility of polynomials. Condition for divisibility of polynomials. Let's see how the condition exists for two polynomials being divided. So for example, I have a polynomial f of x which is divided by another polynomial, say g of x. Then the divisibility condition says that this polynomial can be divided by this polynomial provided we have degree of f of x is greater than degree of g of x. Is how I see the condition for existence of divisibility of two polynomials. Is how I see the condition. Condition for divisibility of two polynomials is only possible when degree of f of x is greater than degree of g of x. For example, if I take a polynomial 2x cubed plus 5x minus 2 by x power 7 minus 4, then clearly I see that the degree of this polynomial in the numerator is 3 and the degree of the polynomial in the denominator is 7. Therefore, I don't have my condition which satisfies here, because clearly in this case degree of the numerator is less than degree of the denominator, in this case 3 less than 7. Therefore, f of x cannot be divided with the polynomial g of x in this case of the example problem. F of x can be divided with the polynomial g of x only when degree of f of x is greater than degree of g of x. And the division is done through the long division method as discussed in the session. Now that we have discussed the divisibility properties for the polynomials, now comes the most important theorem in the branch of polynomials called the remainder theorem. Remainder theorem helps us mostly in finding the remainder when a polynomial divided by another polynomial. You can directly use the theorem to find the remainder without constructing to the long division method. So let's see what the remainder theorem says in its own definition. Remainder theorem. As the theorem says, remainder theorem, this theorem dedicates in identifying the remainder of a polynomial divided by another polynomial. Is the first thing which we note from the theorem called the remainder theorem. Something relates to the remainder indivisibility. If I take a function f of x with the condition that the degree of f of x, the degree of the function f of x is not equal to 0, then let's see what the definition says or what the theorem states for this function f of x. So with the first condition that I take the polynomial f of x with degree of the polynomial f of x being non-zero, then in that case, that is, f of x is not a constant polynomial. In exception to the constant polynomial, if the function or the polynomial f of x is divided by x minus a. Now we all know that this is a linear polynomial because the power of x is 1, and hence this is a linear polynomial with the condition that a is a constant or a real number. So my theorem says that if a polynomial f of x whose degree is non-zero is divided by a factor x minus a or divided by a linear polynomial x minus a with a belonging to set of real numbers, then remainder of f of x denoted by capital R is nothing but f of a, is how I understand the theorem, remainder theorem in its own definition. Here we have the remainder, which is directly the polynomial in which the value a is substituted, and a is nothing but derived from the linear polynomial. For a polynomial f of x with degree being non-zero, if divided by a linear polynomial x minus a for a belonging to any real number, then the remainder of the polynomial f of x is directly f of a, is how the polynomial is related to the constant of the linear polynomial in the divisibility, is what the remainder theorem states. Now let's see an example problem to understand the remainder theorem more better. Let's try to apply the remainder theorem in real life. So coming to the remainder theorem, we have already defined that for any polynomial divided by a linear polynomial, then the remainder is directly connected to the factor of that linear polynomial into the polynomial. So we are going to use that theorem concept when we do certain problems related to remainder theorem. For example, if I have my question which says find the remainder when the polynomial f of x or p of x, when the polynomial p of x equals x cubed minus 3x squared plus 4x minus 1 is divided by x plus 2 is the question. The question is very clear about finding the remainder when the polynomial, which is x cubed minus 3x squared plus 4x minus 1 is divided by the linear polynomial x plus 2. So let's see how the remainder theorem can be applied for this particular example problem. As the polynomial is given to be p of x is x cubed minus 3x squared plus 4x minus 1, the first thing I identify is that this polynomial is not a constant polynomial. The first condition for remainder theorem is that degree of p of x should not be equal to 0. And clearly the degree of p of x is 3, and hence 3 is non-zero. Therefore, it satisfies with the first condition of the remainder theorem. Secondly, the second part of the given question is about the linear polynomial. Therefore, the given linear polynomial is x plus 2. And if I compare this with x minus a as given in the theorem statement, I clearly see that when I express x plus 2 in x minus a form as given in the remainder theorem, I have this x plus 2 which can be written as minus of minus 2. I extract minus out of plus, then one minus sign remains inside the bracket, so that minus into minus is plus, which retains back x plus 2. So the reason why I write this in this form is to extract in the form x minus a. So this a is nothing but the minus 2. Therefore, I have my a, which is minus 2, belonging to the real numbers. The constant, the non-zero constant a is minus 2 in case of this problem. So this is the step 2 of identifying a, step 1 of satisfying the condition of degree of p of x being non-zero, and step 2 identifying the value of a, and step 3 is finding the remainder itself. Now, for the polynomial p of x, when divided by x plus 2, the remainder is f of a, or p of a, or this is p of minus 2. This is strictly by remainder theorem. Remainder theorem clearly says that when a polynomial which is non-zero degree is divided by a linear polynomial, the remainder is f of a or p of a. And in this case, a being minus 2, it is p of minus 2. Without any long division method process, we can directly find the remainder using remainder theorem. So let's see how the remainder can be evaluated for this p of minus 2. Therefore, when I evaluate this, I get the remainder, which is p of minus 2, and p of minus 2 is the value which is obtained by substituting the value of x equal to minus 2 in the given polynomial p of x. Therefore, when I have p of x replaced with x being replaced with minus 2, equally the x gets replaced with minus 2 on the right side. So I have this to be minus 2 whole cube minus 3 of minus 2 whole square plus 4 times minus 2 and minus 1 is what we get when we expand by substitution of x equal to minus 2 on the right side of the given polynomial. When this is further simplified, I get this to be minus 8 minus 3 times of minus 2 whole square, which is 4, and minus 8 and minus 1. And this comes out further minus 8 minus 12 minus 8 minus 1, which on simplification gives 12 times 8, 20, 20, 12 plus 8, 20, 28, 29, which comes out to be negative 29. Therefore, I get the value of remainder for the given polynomial. Remainder of p of x is minus 29 is what I get finally using the remainder theorem. Remainder theorem helps me in finding the remainder when a polynomial is divided by a linear polynomial with the conditions out here. Continue. Now let's see how we can verify the remainder theorem using the long division method, because This is the property which we have used directly through the remainder theorem, which states the remainder is directly f of a or p of a, for x minus a being the divisibility polynomial. So here we're going to see the verification process, whether we really get the remainder to be minus 29 when we just solve through the long division general method. So I have the polynomial, the dividend out here, and the divisor, which we're going to take at this thing. Dividend and the divisor, which when divided gives me x cubed minus 3x squared plus 4x minus 1 when divided by x plus 2. Let's find the quotient and the remainder, most importantly, to verify for the remainder as obtained through the remainder theorem. So as we know through the long division method, as discussed in the previous sessions, x times x squared gives me x cubed. 2 times x squared is 2x squared, which on subtraction gives me this cancelled, and I get this to be minus 5x squared plus 4x minus 1. I just drop in these two down here. Now the next second division method says my x when multiplied with minus 5x gives me minus 5x squared, and hence I just put in minus 5x squared in the quotient, so that this multiplied with this gives me the equal term as in the top, is how we understand the long division method. 2 times of minus 5x is minus 10x, and then when I subtract again, the signs change and this gets cancelled. Plus and minus of the same sign get cancelled, and that is the intention why I make the terms equal through the quotient by adding or subtracting the terms. 10 plus 4 is 14x minus 1. Minus 1 dropped straight down. Now this has to be made equal with x. So obviously it is 14 which is multiplied with x. Therefore my quotient gets added with 14. So that 14 times of x is 14x plus 14 times of 2, which is 28. Again using the same process of subtraction, the signs change and this get cancelled, and minus 1 minus 28 is minus 29, which is the remainder, which is the quotient. And most importantly, when I see the remainder as done through the long division method, I get the value as minus 29, and when I use the remainder theorem with its own statement, I get the value of remainder, which is minus 29, and hence they are same, which concludes that my remainder theorem is very much true to its best. Remainder theorem is most important in finding the remainder of the polynomial's divisibility. Now that we have discussed about remainder theorem and its significance in finding the remainder in dividing the two polynomials, let's try to take that concept more further. Remainder theorem also helps us not only about finding the remainder, but also in verifying for the factorization. If I would like to check for a linear polynomial to be a factor of the given polynomial p of x, I can simply do that also equally using remainder theorem. So let's see how we can use remainder theorem in factorization. Remainder theorem versus factorization. It's very simple to understand the factorization using remainder theorem. So let's see how we can connect factorization with remainder theorem. As we have discussed about remainder theorem, let's recap the definition or the statement of the remainder theorem back again. If a polynomial p of x is divided by a linear polynomial x minus a, it gives us the remainder p of a or f of a, is what we understand. If I get the remainder to be 0, then let's see what will be the special case. If P of A is 0, that is A is the 0 of the polynomial P of x, 0 of the polynomial P of x, which gives us a different concept of understanding the factorization. Therefore, if I have a special case which says P of A is 0, that is with the condition that the remainder is 0, that is when the A is the 0 of the polynomial P of x, then simply when I substitute this value in the remainder, I get remainder as 0. And when the remainder is 0, it comes under special case in the remainder theorem. So in the special case of the remainder theorem with remainder 0, that implies I say this x minus a is a factor of P of x. It acts as the factor of the P of x. X minus a is a factor of P of x. It exactly gets divided with the polynomial P of x. Is how we understand the factorization, then condition related with the remainder theorem. Is how I understand the factors connected with remainder theorem. Now let's take an example problem to understand the concept more better. Remainder theorem versus factorization. If I have a question which says, is x minus 3 a factor of P of x equals x squared minus 5x plus 6. I have a question here which says, is the linear polynomial x minus 3 a factor of P of x equals x squared minus 5x plus 6? Then how do we continue with? Of course, with the remainder theorem. Remainder theorem not only helps in finding the remainder, but also in identifying or justifying whether a given linear polynomial is a factor or not a factor of the given polynomial P of x. So let's see how we can do this with an example problem. As I have the given polynomial to be P of x equals x squared minus 5x plus 6 and my linear polynomial which is x minus 3, I clearly see the condition 1 of the remainder theorem which says the degree of P of x is 2, which is not equal to 0. The condition 1 where the degree is non-zero. And the second thing I find here is my x minus 3 when compared with the factor x minus a clearly says that my a is 3, which belongs to real numbers. So degree being non-zero and the value a belonging to set of real numbers is what is the condition for existence of remainder theorem. Now with these two conditions, let's see what is the remainder for the given polynomials divided one by the other. By remainder theorem, which we have already discussed in the session, if the polynomial P of x is divided by x minus 3, that implies the remainder is f of a or P of a, which is 3. Let's see what is the value of P of 3. P of 3 is when we substitute the value of x equal to 3 in the polynomial in the left side equally on the right side with 3 squared minus 5 times 3 plus 6, which on further simplification gives me 9 minus 15 plus 6, which is 15 minus 5, which is equal to 0. Therefore, my remainder is, when we cancel, I get as 0. Therefore, the remainder is 0. So when the remainder is 0, we have already discussed in remainder theorem connecting with factorization that if the remainder is 0, then the given divisor is a factor or a pure factor of the given dividend. Therefore, x minus 3 is a factor of p of x. It exactly divides is how we understand x minus 3 is a factor of p of x. Is how we conclude the remainder theorem with factorization. Remainder theorem also helps in finding factors and helps in finding the remainder. So let's see what are the factors for this given problem. So when I have the polynomial p of x, when divided by x minus 3, I have my p of x, which is x squared minus 5x plus 6 by x minus 3, which is x minus 2 times x minus 3. This polynomial is a quadratic polynomial or a quadratic function which can be expressed as factors by using factorization. When I factorize the quadratic function, I get the factors as 2 and 3, and therefore this can be written as x minus 2 times x minus 3 by x minus 3. It gets cancelled because it's a factor. And why is it a factor? Because it satisfies the remainder theorem with factorization. Remainder is 0, and hence, because the remainder is 0, the two factors get cancelled. That means x minus 3 is a pure factor of the given polynomial p of x, and the result is x minus 2. Is how we understand the complete concept of remainder theorem connected with factorization. Now that we have discussed about remainder theorem and its various significant facts in the branch of mathematics, let's enter into the next step of the theorems, the factor theorem. Continued from remainder theorem, today's session is about factor theorem. What is a factor theorem? The significance is what we are going to discuss before discussing the theorem itself in its own definition. The importance of factor theorem in the branch of polynomials is that factor theorem helps us in factorizing the polynomials. Remainder theorem helps us in identifying or justifying for the given linear polynomial to be a factor of the other polynomial, but factor theorem helps me in finding the factors directly. Finding out the factors or factorizing the given polynomial is what is the main significance of factor theorem. Let's see how it is possible. The theorem says that if I have, say for example, a polynomial p of x, which I need to factorize. The question here says factorize the polynomial p of x equals x squared plus x minus 12 is how I have this polynomial. So let's see how we can factorize using the factor theorem. Directly through an example problem, let's try to understand the concept more stronger. So in this case, my given polynomial is p of x equals x squared plus x minus 12. It is a polynomial which is non-zero, and I would like to factorize this or express as the product of the linear polynomials. So let's see how we can factorize this given polynomial. Now this quadratic polynomial has its coefficients which are 1, and the coefficient which is 1, and here the coefficient which is negative 12. So I initially pick all the coefficients or the constants from the given polynomial. So once I pick, I extract and identify for that for this given polynomial the coefficients are 1, 1 and minus 12. So with this concept, I take the middle one. The middle term is always the coefficient of x. Now here, the first condition in identifying the polynomial, the quadratic polynomial or any other polynomial in factor theorem is that I make the coefficient of x squared always 1, or the highest degree coefficient should always be made equal to 1. Now this is directly out here with the coefficient as 1, so we need not just make the coefficient 1. Or for example, in case I have 2x squared plus 6x minus 9, then I try to make the coefficient of x squared 1 by taking 2 common, and I get this to be x squared plus 6 by 2x minus 9 by 2. Is how we take the 2 out and then make the coefficient of x squared or the coefficient of the highest degree polynomial equal to 1. Is how I understand the factor theorem condition. So once we satisfy the condition of the coefficient of x squared or the coefficient of the highest degree term being made equal to 1, I try to extract the coefficients. Then the middle coefficient, which is 1, and the last two coefficients, which are minus 12 times 1 is minus 12, is what helps me in factorization. So once I multiply the first and the last factors, I get the value as negative 12. Now the possible factors of minus 12 are minus 1, minus 3, plus or minus, plus or minus, plus or minus, and plus or minus 4. And this is minus out here. So I get the possible factors to be plus or minus 1, because 12 by 1 is a factor of 12, 2 is a factor of 12 with plus and minus both, and 3 is a factor, 4 is a factor, 6 is a factor, and equally 12 is also a factor. So I have possibly here 6 different factors for minus 12 is how I identify the factors. So once I identify the possible factors, then randomly I try to substitute each of them into the polynomial until the value becomes 0. So out of these, I identify the zeros. So which of the polynomials are the zeros is what we're going to identify here. So let's check if this is the 0 of the polynomial. P of 1 squared plus 1 minus 12 is minus 10, which is not equal to 0. Therefore, 1 is not the 0 of the polynomial. Even minus 1 also doesn't. So we randomly try with 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, 6 minus 6, and 12 minus 12. And then whichever is the 0 of the polynomial, that value is picked, and that helps us in factorizing through the factor theorem. Let's try with 2 or minus 2. I get minus 2 whole square plus minus 2 minus 12. 4 minus 2, 2 minus this, again not equal to 0, is what I get here. So here it's again not a 0 of the polynomial p of x given. Let's try with 4 and 3. P of 3 is 3 squared plus 3 minus 12. 3 3 is 9, 9 plus 3 is 12, 12 minus 2, 12 is 0. And yes, P of 3 gives me the 0 of the polynomial. Therefore, x equal to 3 is the 0 of the given polynomial P of x. So I pick this. Next, let me try with 4. Minus 4. So when I pick for minus 4, I get this to be minus 4 whole square plus minus 4 minus 12. 16 minus 4 minus 12 is 0, and therefore even minus 4 is picked. So and so forth. Randomly we go with each of the value of 6 minus 6, 12 minus 12, and then pick the zeros. And here for the polynomial, the zeros being P of 3 and P of minus 4. Even 6 and minus 12 does not give 6 plus or minus 6 and plus or minus 12 does not give the zeros of the polynomials. Therefore, 3 minus 4 are the zeros of the polynomial P of x. Now these being zeros, therefore x minus a is what we have seen in the remainder theorem. If the remainder is 0, then x minus a is a factor of the given polynomial f of x or p of x. So x minus 3 and x minus of minus 4, that is x plus 4, are the factors of p of x. Therefore, my p of x, which is x squared plus x minus 12, can be written as the product of the factors x minus 3 into x plus 4, is how I understand factorization through the factor theorem. Factor theorem is based on zeros of the polynomial. So for the given polynomial p of x, I just make the rule 1, that is coefficient of x squared should always be 1. Coefficient of the highest degree term must be 1, and the rest of the terms can be non-1. Pick the coefficients, multiply the first and last, find the possible factors. For each of the possible factors, identify which are the zeros of the polynomials. Pick those zeros of the polynomials and use the remainder theorem. Then we get the linear factors to be x minus a, x minus 3, and x minus of minus 4, x plus 4, to be the factors of the given polynomial p of x. And therefore, that polynomial p of x can be written as product of those two identified factors through the factor theorem. Factor theorem helps us in factorizing the given polynomial. Factorization through factor theorem. Now let's see a factor theorem applied example problem using the same concept for a polynomial with a higher degree. In the previous session, we have discussed about a polynomial which is a quadratic or with degree 2. Let's try the similar concept through a polynomial of degree 3, a cubic polynomial. So using the factor theorem for, say, a question where I need to factorize the polynomial x cubed minus 6x squared plus 11x minus 6. So let's see how I can factorize this cubic polynomial using the factor theorem. So let me go with rule number 1, where I'll write the polynomial p of x as x cubed minus 6x squared plus 11x minus 6. My first rule is to identify that the coefficient of the highest degree term is 1. So as I identify here, the highest degree of this polynomial is 3 and its coefficient is obviously 1. So I need not make it 1. It's already available with coefficient equal to 1. Is the rule number 1 in the factor theorem. So now that the rule 1 is satisfied, I pick all the coefficients 1, minus 6, 11 and minus 6. So I pick all the coefficients of this given polynomial and then I take the first and the last. My first and last coefficients are multiplied so that 1 times of minus 6 is equal to minus 6. So I get my product of the first and last term is what I do in the rule 2 of the factor theorem. So rule 2, multiply the first coefficient with the last coefficient and I get the value as minus 6. Now for this minus 6, I find all the possible factors for minus 6. As we know that plus and minus 1 is one of the factor for minus 6, and then plus or minus 2 is the possible factor for this. Plus or minus 3 is also the possible factor for minus 6, and plus or minus 6 is the possible factor for minus 6. So I have totally the 4 sets of possible factors: plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now once the rule 2 is satisfied, now comes the next rule about finding the zeros of the polynomial. Using these possible factors, I next find the zeros of the polynomials. To find zeros, In order to find zeros, I just substitute the values in the polynomial so that when I take 1, when substituted in the polynomial, let's see what would be the possible factor. So when 1 is substituted out here, I get this to be 1 cube minus 6 1 square, 11 times 1 minus 6, which on further simplification gives 1 minus 6 plus 11 minus 6, which gives me 12 minus 12, which is 0. Therefore, 1 is the 0 of the polynomial because it gives the value 0 when substituted in the polynomial. So one of the polynomial identified here with 0 is x equal to 1. Next, let's see how we can proceed further with this. Now let's try with the second possible pairs of factors plus or minus 2. So I pick one of the sign, that is plus 2, and see if that is the 0 of the given polynomial p of x. So I get this to be p of 2, which is 2 cube minus 6 times plus 11 times minus 6, which on further simplification gives 2 cube, which is 8, 8 minus 6 times 4, which is 24, and plus 22, which is 24 minus 24, because this gives me minus 30, and 24 plus 8, and therefore I get this to be 22, 11 times 2 overall, which gives me 0 on complete simplification. Therefore, I clearly identify that even x equal to 2 is the linear factor, or x equal to 2 is the 0 of the given polynomial p of x. Similarly, I try with the other pair. P of 3, when I check for the 0 of the polynomial 3, I just substitute p of 3 and I get this to be 3 cube minus 6 times 3, 11 times 3 minus 6. And this on further simplification gives 3 cube, which is 27, minus 6 threes, which is 18, 11 threes 33 minus 6, which on further simplification gives 27 plus 33, which is 57 60 into the square. So 6 times 9, which is 54. So I get this to be 27 minus 54 plus 33 minus 6, which is 54 plus 6, 60, 37 plus 27, 60. So 60 minus 60 also equally gives me 0. And therefore, even 3 is the 0 of the polynomial p of x. Similarly, we try to test randomly through even 6. And then finally, because the degree of the polynomial is 3, I search for 3 0 polynomials. So now that I got these 3 polynomial zeros, I just directly have the remainder theorem, which says if f of x is 0 or p of a is 0, then directly we have x minus a is the factor of the given polynomial p of x. 1, 2, 3 are now the zeros of p of x. Now 1, 2, 3 are zeros of the p of x. Therefore, x minus 1, x minus 2, x minus 3 are the factors of p of x. These 3 are the factors for p of x by using remainder theorem. Therefore, p of x, which is x cubed minus 6x squared plus 11x minus 6, can be written as x minus 1 times x minus 2 times x minus 3 is how I get the possible factors. Finding the factors or factorization using factor theorem is possible for any polynomial of degree n. Now that we have discussed about the 2 important theorems, remainder theorem and factor theorem, now comes the new concept of the algebraic identities. Every part of algebraic identity is useful in solving many mathematical problems. So let's see what are the possible algebraic identities. Algebraic identities are the formulae which are said to be universally true for any variable. The left hand side will universally be equal to the right hand side, however, be the value of the variable belonging to set of real numbers. So let's see some of the algebraic identities. The most important identity, as discussed in the lower classes, is that when I expand x plus y whole square, it must be universally equal to x square plus y square plus 2xy. Identity number 1 is how we see that this is universally equal to this, and this is true for all x, y belonging to the real numbers. This holds true for any variable x and y belonging to the real numbers. Similarly, I have the other identity which says that when I have x minus y whole square, it can be universally identical to x square minus 2xy plus y square for all xy belonging to the real numbers. Similarly, a plus b whole cube, a cube plus 3a square b plus 3ab square plus y cube. This is true for all x and y belonging to real numbers. Next, x minus y whole cube, which is x cube minus 3x square y plus 3xy square minus y cube, which is true for all x and y belonging to R. Next, x square minus y square is said to be identically equal to x plus y into x minus y, is how I identify the identity using x square minus y square equals x plus y into x minus y. Next, x plus a times x plus b by introducing the two new real numbers a and b can also be expanded and to be identically equal to x square plus a plus b times x plus ab, is how we identify for the two real numbers. For a and b belonging to the real numbers. Similarly, we have many other algebraic identities like x cube plus y cube, which is said to be x plus y into x square minus xy plus y square, is also one of the identity which makes this equal to this. X cube minus y cube is x minus y into x square plus xy plus y square, is how so on and so forth we have many algebraic identities. What if I have three variables introduced, x, y, z whole square? Then this also can be identified to be an identity, algebraic identity, a square, x square plus y square plus z square, 2xy, 2yz, 2xz for all the real numbers x, y, z, is how I identify the identity x plus y plus z whole square. What if I have x plus y plus z whole cube? This also has its own property. A cube plus b cube plus c cube plus 3ab into a plus b plus c cut. Now let's see the continuation of the algebraic identities. The next algebraic identity identified is x cube plus y cube plus z cube minus 3x yz is said to be directly equal or universally identically equal to x plus y plus z times x square plus y square plus z square is how we identify this example problem. Let's see how we can continue in identifying the applications of algebraic identities in solving mathematical problems. Say, for example, I have a problem which says factorize 8x cubed 27y cubed plus 64z cubed minus 48 144 xyz is what is the given problem, and I would like to expand to factorize this given polynomial in three variables x, y, and z. So let's see how we can factorize this polynomial, which is in more than one variable, x, y, and z being the variables, using the concept of the algebraic identities. Now, the given problem, which is 8x cubed plus 27y cubed plus 64z cubed minus 144 xyz, can clearly be written as 8x cubed, which is 2x whole cube, plus 27y cube, which can be raised to 27 being 3 cube, 3 times 3 times 3, can be written as 3y whole cube, so that this becomes a number, the perfect cube of 3y. And similarly, I have 64, which can be written as 4 cube, and this can be written as 4z whole cube. So the given polynomial can be expressed as 2x whole cube plus 3y whole cube plus 4z whole cube minus 144, which can be split as 3 times 2x times 3y times 4z. I can split this 144 xyz as 3 times 2x, which is the first term of inside the cube of the first term, and then 3y, which is inside the cube of the second term, and 4z, which is inside the cube of the third term. And then the reason why I expand and put it into this form is with the algebraic identity which is identified here. We know that the algebraic identity x cubed plus y cubed plus z cubed minus 3xyz is identically equal to x plus y plus z into x squared plus y squared plus z squared minus xy minus yz minus xz. So using this algebraic identity, I compare the left hand side of this identity with the given problem. Now clearly I see that in place of x I have 2x, in place of y I have 3y, in place of z I have 4z, so that this whole left hand side of the algebraic identity can be equally substituted for the right hand side of the algebraic identity, where my x, which is 2x, I have my this 2x with y with 3y, and my z with 4z, which comes in the first factor x plus y plus z, and then x squared, which is 2x whole square, and y square, which is in place of y 3y whole square, and my z, which is 4z whole square, minus xy, your x being 2x and my y being 3y and z being 3z are equally substituted for x, y, z in the main algebraic identity. So 2x 3y minus 3y 4z minus 2x 4z is what we get when we expand through the formula. This can be further simplified so that I get this to be the first factor being 2x plus 3y plus 4z, and my second factor being 2x whole square, which is 4x square, and 3y whole square, which is 9y square, and my 4z whole square, which is 16z square, minus 2 times of 3, which is 6. Therefore, I get this to be minus 6xy minus 4 3 is 12. So I get this to be 12yz, and 2 times 4, which is 8. Therefore, I get minus 8xz is what I get as the factors for the given polynomial. Factorization of the polynomials which have more than one variable is done using the algebraic identities. This algebraic identity helps in factorizing this given problem. Applications of algebraic identities is to factorize the polynomials. Now let's see the other types of applications of the algebraic identities in solving many mathematical problems. As we have seen with the previous case of one of the algebraic identity which helps us in factorizing, the algebraic identities also help us in solving many problems which involve multiplication of two numbers. So let's see one of the application. The applications of algebraic identities is the topic for today's session. So for example, I have a question which says, find the product of 104 times 96. Then we can do this by using the calculator or with general multiplication, but without using the simple multiplication process, also we can just multiply the two numbers using the algebraic identities. Interesting, but yes, it can. Let's see how. Let's take the given product which needs to be simplified. I have this to be 104 times 96, which I need to multiply. So in order to do this, what I do is I try to express this in one of the algebraic identity form so that I can use it as a formula, and then the simplification becomes easier. So in this, generally what we do in these kind of problems is that we try to express through the standard numbers. 104 I can express in standard form as 100 plus 4, so that this 100 is easy to multiply or even to divide or add with other number. So the standard base here being 100 is taken for 104, so that 104 is written as 100 plus 4. This stands as the standard fixed number taken out here. Similarly, 96, if I express through the standard form, I can write it as 100 minus 4. So 96 can be written as 4 units short or 4 numbers short of 100, and 104 is 4 numbers ahead of 100, and therefore 104 is 100 plus 4 and 96 is 100 minus 4. The reason behind writing in this form is that we strike seeing this in the form x plus y times x minus y. We all know that x plus y times x minus y is identically equal to x square minus y square, or a plus b times a minus b is a square minus b square. Therefore, I get this to be a plus b times a minus b. Using this formula, I get this simply 100 square minus 4 square is what is obtained through the algebraic identity x plus y times x minus y is identically equal to x square minus y square. And this comes out to be 100 square is 10,000 minus 16. So I get this to be 100 square, which is 10,000 minus 16, which 9984 is the answer. Therefore, I get the answer to be 9,984. Therefore, 104 times 96 is 9984. This is very interesting because without using the general multiplication process, I can find the product of two big numbers using algebraic identities. This being one of the example case. Now let's see if this value as obtained through the multiplication of two numbers using the algebraic identity is verified to be true. Let's do the verification process by using the general multiplication of two numbers. As clearly we see here, I see that 104, when I multiply with 96, I get this to be 6 times of 4, which is 24, and 6, which is 2. 6 ones, 6. Next, 9 fours, 36, 9, 3, and 9, which when added gives me 4, 8, 9, and 9. And this comes out to be 9984, and this comes out to be 9984. Therefore, verification is true, is what I make the learning outcome. The learning of the product of two numbers using algebraic identity is very much true as compared to the general multiplication. Applications of algebraic identities in real life. Say for example, I have another set of an example which says simplify the value 99 whole cube. How do I simplify this without generally multiplying the numbers 99 times 99 times 99? Of course, we can simplify this using the algebraic identities. Let's see how we can use algebraic identities to solve this particular cube number. Now, as we see the question, I would like to simplify this 99 cube. Then clearly I write this to be 100 minus 1 whole cube, as discussed in the previous example, that we take the standard number as the base. So here the fixed standard number is 100, which is taken to convert the given number 99 in terms of 100. Therefore, the 99 cube can easily be written as 99 for 100 minus 1 whole cube. Now, once this is converted into 100 minus 1 whole cube, we see that immediately it gets compared with the identity x minus y whole cube. What is x minus y whole cube? It is an algebraic identity which expands to a cube minus 3a square b plus 3ab square minus y cube. Or this can also be written as, this expansion is also equal to a cube minus b cube minus 3ab into a minus b. Both are the same expansions. Or this formula can also be written as x cube minus y cube minus 3xy times x minus y. Both mean the same identity for x minus y whole cube. So I'm going to use the second form of the identity for expanding x minus y whole cube, that is 100 minus 1 whole cube, indirectly 99 cube. So let's see how the expansion proceeds. So x, I treat 100 as x and I treat 1 as y, so that this gets reduced to x cube, which is 100 cube minus 1 cube minus 3xy into x minus y, is what we get when we expand the given expansion. The 100 cube is 10 lakhs minus 1 cube is 1, minus 300 times 99 is what we get, which on further simplification gives us 1 lakh, 10 lakhs, minus 1, minus 9 threes 27, 9 threes 27, 29 of 0, which further simplifies to give minus 29701. Now we need to subtract these two numbers to get the value for 99 whole cube. As we know that the subtraction of 10 lakhs is what we get when we subtract this number from this. Therefore, my answer for 99 cube, which is multiplication of 99 3 times, is directly 970,299 is what we get as the value using the algebraic identity. Applications of algebraic identities in solving the problems, the math problems in real life.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.